Thank you. My name is Giray, and I'm a PhD candidate in ETH Zurich in Software Research Group. And I'll talk about some reliability problems of real DRAM chips today. So, read disturbance is an important reliability and security problem in DRAM, and it's getting worse. And as a result of that, existing mitigation mechanisms are becoming extremely expensive. And our goal in this work is to understand the spatial variation of this vulnerability within a DRAM chip across different rows, and to leverage this understanding to improve the existing mitigation mechanisms. And to this end, we conducted an experimental study on 136 DDR4 DRAM chips. We test all rows in a bank and a bank from each group, and we observe a large variation in the necessary activation count to induce the first bit flip. And we use this, we analyze this data, and unfortunately we cannot find any correlation, a strong correlation between the spatial features of a cell and the vulnerability level. But we use these experimental results to adapt existing mitigation mechanisms and reduce their performance overheads. This can be a mechanism implemented in the memory controller or in the DRAM chip, and we show some significant performance improvements. So as a quick background, we have these DRAM chips in our computers today, and a bunch of chips in a DRAM rack, and within each DRAM chip we have several banks, and each bank consists of multiple subarrays, and DRAM cells are organized in a two-dimensional array here and internally accessed in a DRAM row granularity. So to access data in a DRAM row, we need to first activate the row or open the row to fetch the data into the row buffer, and then we insert the column accesses from the row buffer, and then we need to close the row to access another row. And if we open this row and then close it and do this many times, we see some bit flips in the nearby rows breaking the memory isolation. And these errors are called RowHammer bit flips. And there's another mechanism that happens when you keep the row very open for a very long time. It's called row press bit flips. It's also discovered this year earlier. And as a result, repeatedly opening and closing a DRAM row or keeping a row open enough causes bit flips in nearby cells. So we want to understand the special variation of this, because this disturbance gets really worse as the DRAM chip density increases. We need inducing bit flips is much easier today than they were like a decade ago. And our goal is to understand the spatial variation and to use that to improve the mitigation mechanisms. And this is our infrastructure that we test real DRAM chips. We have fine-grained control over DRAM commands, timing parameters, and temperature. And from our experimental study, we get two key takeaways. One of them is the disturbance vulnerability significantly varies across DRAM rows, and the other one is there is not a strong correlation that we observed. It doesn't mean there's none. This is a histogram of the minimum hammer count to induce the first bit flip across different rows. So we observe that weakest rows can observe bit flips at 4K activation count, and some other rows, many other rows, does not observe any bit flip until like above 24K. And when we repeat this experiment on different manufacturers, so manufacturers are SK Hynix, Micron, and Samsung from left to right, we observe a large variation in all of them. And we also looked at the effect of row press, where we increase the time that the row is open from 36 nanoseconds to 2 microseconds. And we observe that this effect reduces the minimum hammer count that you need to induce the first bit flip. And it still can reduce the variation. It also can reduce the variation HC first distribution. But in Samsung module especially, we still see some significant variation across DRAM rows. Okay, so we looked at the correlation between the DRAM rows with disturbance vulnerability and the bank address bits, subarray address bits, row address bits, and a row's distance to the local sense amplifiers. And we observed in a small fraction of DRAM chips that there is some correlation. A few special features exhibit more than 0.7 F1 score in predicting XC first, but it is not very reliable to implement it in a security domain. So we come up with the mechanism called SVART, Spatial Variation Aware Disturbance Mitigation. It dynamically adapts the aggressiveness of existing mitigation mechanisms based on the row under attacks vulnerability level. And we basically split DRAM rows into several vulnerability level bins, and to do that, we need to only maintain a few bits, around like 4 bits for each row. And we can store these rows in the memory controller or among the parity bits in the DRAM or in a DRAM row itself as normal data. And we can implement this mechanism in the memory controller or in the DRAM chip because it's not very costly. And we did a performance evaluation using Remulator 2.0 with some realistic system configuration. We tried 50 different 8-core multi-program workloads from these benchmark suites. And we tested SWARD with 4 of the best mitigation mechanisms. And we tested different, we basically projected the minimum hammer count needed to induce the first bit fill-up for future and sweep that parameter. And this is a performance result that we have for RowHammer. The bottommost curve is the original proposal, and you can see that it induces a lot of performance overhead as the vulnerability gets worse. And we can reduce this performance overhead. And we can do this for all 4 mitigation mechanisms. So in conclusion, we did this experimental study on 136 DRAM chips, and we observed a large variation, and unfortunately not a strong correlation. We are still working on that. We propose this mechanism that dynamically adapts the aggressiveness of mitigation mechanisms, and it can be implemented in DRAM chip or the memory controller, and it reduces the performance overhead significantly. So as part of future work, we need to provide a deeper understanding of the irregularities in row addresses and column addresses and the variation across columns as well. And we need to find better correlations to reduce the hardware cost of SWARD. And also we need to study the RowHammer mitigation mechanisms in a greater detail so that we can also reduce their hardware cost in addition to performance cost. And this is the end of my talk. I hope I'm in time.
Are there any questions for Giray?
Very nice talk, thanks.
Thank you.
You talked about finding correlations, and it seems like you're expecting that there's going to be a correlation and you just haven't found it yet. What's your intuition for why there would necessarily be a correlation?
Yeah, definitely. So what we observed is actually there's a large impact of the manufacturing process variation. So that's part of like why we don't see any strong correlations. And the reason I expect that is because of some design decisions made in the DRAM chip. I talked about subarrays in a DRAM bank that are splitted by local row buffers, and we observed that. Actually, I can show it here. For example, when we look at the bit error rate, we observe some repeating patterns, and we suspect that these can be because of those boundaries nearby the I/O circuitry, basically. And the reason is that when you do double-sided, basically you have a victim row and you have aggressor rows in the bottom and top, so you can disturb that victim row from both sides in many rows. But for the rows at the edge, you cannot do that, right? You can only disturb from one side. So we're suspecting that this is an artifact of that and an artifact of some other things as well. But yeah, we just saw like bit error rate variation in this way, in repeating patterns, so we suspected there's some correlation. But when we look at how the minimum hammer count needed changes across rows, it's most like flat and some uniform distribution, so we couldn't find it. I hope that answers your question.
We have time for another quick question if anyone has anything.
So I think like can you go to the almost one of the last slides on the performance on the different, yeah, there. Is there a reason that the performance overhead improves a lot more for Blockhammer, Para, and RS than Hydra?
Yeah, that's That's really a good catch. So it's only 2.7% here, right? The others are like some X's. So the reason is that this is the Hydra mechanism proposed by Croatia et al. In ISCA 2022. So how this mechanism works is that so you have some counters implemented in the memory controller, and there is a counter cache here, but you put all the row activation counters inside the DRAM chip actually. So what happens when we go very low thresholds is that the dominating factor of the performance overhead is not performing the preventive refreshes, but it is actually the data communication between or fetching these counters to this cache. So basically there is a eviction and fetching set of events going through this between cache and the row count table. And this data movement is creating most of the problem, and unfortunately we couldn't address this in this proposal, so it is weak for Hydra, but for other mechanisms, yeah, we have good performance. Does that answer?
All right, thank you, Giray.
Thanks.